So, welcome to problem solving session for computational commutative algebra. I'm Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 4, that is problems related to module localization, Nakayama Lemma and spectrum. Okay, so let us start with our first problem. So, question 1, that let R is equal to Z, so ring of integers, and M comma N are some elements in R, that is M and N are some integers, and we take this map F from R to R, multiplication by M, so that is F of A is equal to M into A for all in R. Okay, so this is a map of modules, map of in fact Z modules or R modules, since our Z is R here. Okay, note that this is not a ring homomorphism, because in ring homomorphism we need to have 1 goes to 1, but here 1 is not going to 1. I mean, of course, if M we choose, here we have chosen this two elements, so if we choose M to be 1, in that case it is, but in general for any given integer M, this A going to M into A is not a ring homomorphism, because we need 1 goes to 1 for map to be a ring homomorphism. So this is module map. I will give a quick definition of module map or R linear maps and so on. And now let I be the R ideal. So R ideal means I is an ideal in R N. So now we chose these two elements. The M is used to define a map, and N we are considering ideal generated by this N. And we have to check whether it is true or false, and the statement is the kernel of the map R mod I going to R mod I induced by F, okay, is isomorphic to an R module this GCD of M comma N quotiented by N. And any guesses whether this is true or false? So let me just first quickly give you the definition of R module homomorphism. So definition that let M and N be R modules. Okay, so F from N to R is called an R module homomorphism, or R linear map. It is also called R linear M to N, R linear map. If F is group homomorphism, so M and N are R modules. So M and N has group structure. So it's F from M to N is group homomorphism, and F of Rx is R into F of X for all R in R and X in M. Okay. So now this, when I write this is module multiplication in M. And when I write this is module multiplication in N. Okay. So this is R module definition of R map. So here what I have, F from R to R. Okay. Let me write again, F from R to R such that A going to M into A. Okay, and now they are saying that F tilde is induced map from R mod I to R mod I such that A bar going to M A bar. Okay. This is the map, and they are saying that kernel of this map, this F tilde, what their claim is, they're asking that if kernel of F tilde is isomorphic to this GCD M comma N quotiented by N. This is their question. So any cases whether this is true, false, or what it is? Just, oh, you have written something. Any cases? Okay, so let me just give you a quick example and we see like what exactly it is. So let us take some examples. So F from Z to Z, okay? They are asking this question for any MNN. Okay, so we can choose some MNN and see how map looks like, how kernel behaves and so on. Okay, so let us just start with some examples. We will see few example and see how or whether this is true or not. And if not, then what exactly is the structure of this kernel if it is not true? Okay, I mean, they're asking whether this kernel is related to this GCD of MNN which we are choosing in the beginning. Okay, so let us see this. I'm just writing Z instead of R to get the clarity. Okay, I mean, we know that R is Z, but I want to write Z for to be clear. So let us define this map 7A. Okay, uh, this is module I like Z module homomorphism. This is that is not a problem. Okay, it satisfies this condition, these two conditions here. That it is group homomorphism, it satisfies addition and ever so on. And the linear map also works here. F of, I mean, it will work because what is R into A? F of R into A is 7RA, which is R into 7A, and so on. So that's not a problem. So this is Z module homomorphism. And let us choose this N to be 35. Or any number you can choose, that's not a problem. But I'm just choosing 35. Then now define this F tilde from Z mod 35 to Z mod 35. And how it looks. Where A bar is going to now 7A bar. Is it clear? The map, please let me know if there is any problem. And so if I want to find the kernel, so for any B in Z mod 35, B is now going to 7 into B bar, right? So I want, so if I want, if A bar is equal to 0 bar or F tilde of A bar is equal to 0 bar, this implies that this 7A bar is 0 bar in Z mod 35. Okay. And when this is true, that when can I have this? So it implies what? That 35 divides 7A bar. So what can we say about this? So 7 into A bar. So we anyway have 7. So 7 is prime. And so we can have this, that 5 divides A bar. Okay, so this, sorry, not A bar, 7A. So 5 divides A. Okay, since 7 is a prime, I can remove it. Okay, so this implies that kernel of this F tilde, this is in fact exactly true. I mean, this equality holds. So for now, what we have is that if it is in kernel, that 5 divides A, so it is of the form 5 into A bar, where A bar is in Z mod 35. I hope you understand what I'm writing here. So this kernel of F tilde therefore is ideal generated by this 5 quotiented by 35. And is this equal to GCD of 7 comma 35 mod 35? Is this equal? No, right? What is GCD of 7 comma 35? It is 7. And this 7 and 35 are not equal. Even the equivalence classes of 7 and 5 in Z mod 35 are not equal. So these two ideals are not equal. Uh, is it clear what I'm saying is? At least let me know that, yeah, you can hear me and what I'm saying is understandable. Okay, so therefore this statement is not true. Okay, so this is not okay. So this is this is false because this is not happening in this example. But what exactly is this kernel then in general? So okay, it's okay that we could get that this is not true. This kernel need not be equal to. So this is not equal. In fact, this is not equal. So just 7. So what exactly this nature of this kernel is? How we can see that how the kernel looks like. So in general, if I take any map f from Z to Z, such that A going to MA and the induced map f tilde from Z mod NZ to Z mod NZ, such that now this 1 bar is going to M bar here, in fact. Okay, we can define this, or A bar going to M A bar. Okay, so 1 bar I'm just explicitly writing here. Okay, so what we have to find the kernel. How exactly the kernel of this F tilde look likes. Okay, to find this. So when I choose some A bar in this Z mod NZ bar, A bar in Z mod NZ, then if this A bar belongs to, just I'm following the steps, but in general fashion, like we did the same thing here. Okay, if A bar belongs to kernel of this F tilde, then what does this mean? This means that this MA bar is, that is F tilde of A bar is equal to 0 bar. That is, this MA bar is 0 bar in Z mod NZ. Okay, so this implies what? N divides this MA. A in Z such that MA in NZ. Yes, exactly. But can we explicitly give expression that what that element is? Okay, so we are trying to find that. So this is clear. So what does this mean? That this MA is some NB for, or let me just write this so that I don't confuse myself. Okay, for some Q in Z. This is just a definition I'm following of integers and congruence classes and so on. Okay, so let GCD of, let D is equal to GCD of this M comma N. Then this M is what? dm dash, and this N is dn dash. Okay, so from this equation here, I get this dm dash A is equal to dn dash Q. So since D was a GCD, I can remove it. And we still get this, that M dash A is equal to N dash Q with GCD of M dash and N dash to be 1. Okay, but this implies what? That N dash divides this LHS. So this implies this N dash must divide M dash A also. Is this clear? But GCD of this N dash and M is 0. Sorry, is 1. GCD of M dash, okay, and N dash is equal to 1. So this implies that N dash divides actually this A. So this implies that this A bar must belong to this ideal generated by A must belong to this ideal generated by N dash. And what was this N dash in fact? N dash was this D. So from here N dash is N by D. D was GCD of M comma N. Okay, so in fact, therefore, let me write again. It is GCD of M comma N. So therefore, this kernel of F tilde is in fact this ideal NZ plus N dash Z quotiented by NZ, or this is just simply ideal generated by NZ. Okay, any doubts here? How we did? We just followed. So this is definitely not true, but this is not true, but definitely this is the expression of kernel. Okay, this of or this map. Okay, so it is in fact n by GCD of M and N. That will give me the elements in kernel. Or any doubts here? Please let me know if there are any kind of doubts. A in Z and MA in NZ. Okay. Okay, but it is clear, right? MA in NZ, I mean, that imply that this GCD must be in general, but is there any doubt in this? Okay, clear, great. Okay, so please, if you have any doubt, let me know. Otherwise, we can move to next question. Okay. Okay, so I will move to next question. And question 2 is that is KT, this fraction field of fractions of KT, is a Noetherian KT module. Okay, this where this K is filled. Okay, so this is the question that if this KT, so KT, if you don't know, KT has this form f of t by g of t. Okay, so this is and they are asking whether this KT is Noether this KT is this Noetherian KT module. So the fraction field of a polynomial ring is a Noetherian module over that polynomial ring. That's the question. And we are in a polynomial with one variable. So any guesses? So we have this result from the that if R is Noetherian, then and M is R module, then M is Noetherian R module if and only if M is finitely generated as an R module. Okay, so any guesses whether this is true or false or uh, any kind of guess which you have? You know what is finitely generated as an R module means, right? So, you know. Okay, so is this true then? Shubhadeep, when you said yes, do you mean this statement is true? Or you know that it is a module? Okay, so finitely generated means there exist finitely many elements. So therefore, it's similar to something being finitely generated as a vector space, finite vector space or finite dimensional vector space. Okay, so it is like M is okay. So M is finitely generated, whatever finitely generated R module. Let me just quickly. If there exists G12, very bad. Let me write F1 to Fk in M such that for all F in M, F is equal to summation AI Fi, I from 1 to K, where AI belongs to R. So every element of M, I can write the linear combination of that generating set and so on. So this is the definition of finite generation. That is okay. So can you, do you feel that this is KT module? I guess it's fall there in infinitely price sensitive. Exactly. This is like what Shubhadeep said is correct. There are infinitely many primes. In fact, in the very first problem solving session, we already proved that this KT is not finitely generated as even module, as an KT algebra. Okay. We proved this. And again, as he said, we have infinitely many primes. We did exactly the same. We chose some elements F1 by G1, Fk by Gk, if you remember. We considered this and we proved that and as he said that there are infinitely many primes, in fact infinitely many irreducible elements in KT. We can take this we can even out this denominator here and choose an irreducible not equal to any of the factor of this Gi, and we can see that if H is such element such that no irreducible factor of Gi belongs to no irreducible factor of Gi divides H, then 1 by, we cannot write 1 by, we cannot write 1 by H as polynomial in, I'm talking about algebra, okay, polynomial in polynomial combination of this F1 by G1 to Fi by Gi and so on. Okay, this I completely did in very first like problem solving session. You can see that. So this KT, the field of fractions, is not even finitely generated as KT algebra. Okay. So forget about the module. When we say something is finitely generated as a module, that is even a stronger condition than saying that something is finitely generated as an algebra. Because when, so for example, just see this, that this KT is, the generators are, let me say that this K1 to Kn is finitely generated as in K algebra, right? It is generated by x1 to xn as an algebra. But this polynomial ring kx1 to xn, or let us take x by, it is generated by this x. But this polynomial ring kt is not finitely generated as a k module, right? It is generated by all this 1 t, t square, so on, t power k. So when we say something is generated as algebra, it might need, it in most of the condition needs lesser number of generators compared to when we say something is finitely generated as a module. Okay, so this we already saw that it is not even finitely generated as an algebra. So this cannot be finitely generated as a KT module. Understandable what I'm trying to say? That when we say something is a finitely generated as a module, it is stronger condition than saying that something is finitely generated as an algebra. And we already proved that this is not finitely generated as an algebra. This implies that KT is not a finitely generated KT module. Is this okay? Okay. Uh, Divya, is it okay? Oh, okay. I hope if you have any doubt, please let us know. And if you feel any doubt in the previous argument which we did, uh, please write that. Okay, great. So please uh, feel free to ask. But this is definitely not a finitely generated as a K module or KT module. Okay, so let us move to next question. So let x is equal to spec of z1 by 2. So this is localized ring. I will give a definition. A subset of y is equal to spec of z. Okay. And we have this true or false, that we have to check whether this spec z1 by 2 is an open subset of spec z. This is the question. And when we are writing spec, we mean Zariski topology. Okay. So what are the elements of Zariski topology? They are, this we, so spec R, I'm just writing spec R with Zariski topology. And Vi is equal to all those elements P in spec R such that I is contained in P. These form closed set of this Zariski topology, and this is something called as Di. It is what? It is spec R minus Vi, or it is in fact this P in spec R such that I is not contained in P. And this form open sets of Zariski space. Okay, and under Zariski topology of spec R. So is this clear? So they are asking that we have to check this spec R is an open subset of spec Z. So we have to show that this spec Z1 by 2 is open in spec Z or not. Okay, so does this is D of I for some D of I or any element, in fact. Okay, we can, instead of this I, we can just choose some element. Okay, this also makes sense. Just I'm writing here D of some element F, where you just have to write this, that F belongs to this element P and F does not belongs to P. Okay. So for element, so at least for some element or ideal or some radical ideal, whatever, can we write? Exactly. So as Subhadeep pointed out, it is Z of D of 2. Okay, D of 2, element 2 or D of ideal generated by 2. But before that, what exactly this Z 1 by 2 is? So it is S inverse Z, where S is 1, 2, 2 square, and so on. Okay, so this is multiplicative set. And element of the are of the form sum A by 2 power R, where A belongs to Z and R belongs to N. Okay, so this is the set which we have, and in the lectures we have already seen that we have this proposition. As Subhadeep said, is completely correct. I'm just pointing out the proposition results and some definitions here so that it becomes clear for those who don't know. And it is suppose multiplicative set. If U is multiplicative set and R is ring, then okay. They have that for any R ideal I, U inverse this, U inverse, when I write this is localization, is if and only if U intersection I is not empty. Okay, when I write this U inverse I, I'm saying it U inverse I, but it is just this elements of the form A by U, where let me write this as capital U to avoid confusion. U such that A in I and U in U. So it is like we are inverting the element from this multiplicative set U. Okay, and note that 0 does not belong to multiplicative set. Okay, that is our condition which one should follow. So let P subset of R be a prime ideal. So P is prime ideal. Then such that P intersection U is empty. Okay, P is not intersecting with that multiplicative set U. Then this U inverse P is prime ideal in this U inverse R. Okay, so prime ideals remain prime in this localized ring only if the intersection of that prime ideal in the, if I can say, base ring does not intersect with the elements, does not intersect with the multiplicative set which we will be inverting. Okay, and third is that it is kind of converse of the second part, that conversely if Q is prime ideal in U inverse R. Okay, now we are in this localized ring, that, and we are saying that it is prime in that ring. Then this U inverse of Q intersection R, when I write this, I'm taking like this inverse image of this natural map R going to S inverse R, where 1 goes to 1 by, sorry, A S goes to S by 1 and 1 also goes to 1 by 1. Okay, so it is like when I write Q inverse R, let me use U since I'm working with U. Okay, so this Q intersection R is pre-image of this prime ideal Q, and they say that it is exactly equal to it is Q, not Q, I can say P, where sorry, is U inverse what? Q is prime ideal, then U inverse of is Q. Okay. So it is like I have some U intersection Q is ideal in R, and when I take U inverse of that, so I was here Q, then I came back here, it is suppose some P, and when I again go here, then this U inverse P, then these two are actually equal. But that happen when this Q is prime ideal for any. So this is the converse, sorry, let me just put it here. Okay, so that's what the results which we have. And so we have to see how this take off. So in short, we have this, that prime ideals of Z1 by 2 are in one-to-one correspondence with prime ideals of Z such that it does not contain 2, right? Because anyway, we are having prime ideal, so 1 anyway does not contain that prime ideal. And since we have prime ideal P, if some power of 2 belongs there, then 2 must belong there. So it is saying that 2 does not belong there. Okay, so this prime ideals using this 2 and 3, using 2 and 3, we can say that prime ideals of Z localized at this multiplicative set 1, 2, 2 square and so on is in one-to-one correspondence with the ideals Z such that it does not intersect with this. This intersection must be empty. Okay, so if I want to write this, then spec of Z1 by 2 is actually all those P in spec Z such that 2 does not belongs to P. Okay, so these imply what? This is D of 2, right? This is D of element 2 or D of this ideal generated by 2, doesn't matter. Okay, which is spec of Z minus V of 2. So by the definition, since D of F are open sets of spec R for any F in R, we know this, therefore this spec Z 1 by 2. Yes, exactly. Okay. Just spec 1 by 2 is our open subset of spec Z. Okay, and as Shubhadeep said, like all the primes ideals in Z which are generated by 2, 3, 5, 7 and so on are prime ideals in this. In fact, 0 is also prime ideal in this here because this is integral domain in fact. Okay, so this is just, so we know spectrum of Z is this ideal 0 and ideal generated by P said that P is prime, and we are just omitting this ideal generated by 2. So we can just simply write it as 0 comma P such that P is odd prime. Okay, since it was 2, we have this liberty to write it as a P as a R prime. So in fact, as in general, the result is that if R is some ring and okay, so this is clear, right? And in fact, this is, or if I want to write that, or P says that P is not equal to 2, P is prime. Okay, just to avoid any confusion. And if I take any F in R, then this DF is isomorphic to this R1 by F. Okay, and this R1 by F is all this a comma a by f power r, where a is in r, f power r, so and r in n. When I write n, it includes 0. Okay, so this is true for any given element f of a ring, of course non-zero. Is this understandable? I mean, okay, the same argument follows, because I want it will be in one-to-one correspondence with ideals which does not contain that element f. Then it becomes d of f, and so on. I mean, it is clearly followed from the definition. Okay, and if you have any doubt, please let me know. But this is quite straightforward, that this is true for any element f. So instead of this 2, if I had 3 or 6 and so on. So in case of 6, I will have to remove two prime ideals, 2 and 3, to have this. Okay, so in multiplicative case, we have to remove the elements, I mean, all the primes which contain that element, if you understand what I'm saying. Okay, so it is, for example, I'm saying that spec of z 1 by 6 will be this spec z minus ideal generated by 2 and ideal generated by 3. 5, 7, 11. What does that mean? What is the question? Yes. I mean, you were saying that it is the spectrum contains ideals generated by 5, 7, 11, and so on. Okay, understood. Yeah. So as he pointed out, that's correct. So it is like we have to omit all the prime ideals which contain that element. Okay, I mean, it is definitely the definition of this. This exactly we are following. Nothing else. That f should not belong to that prime ideal. So if we know 6 belongs to ideal generated by 2, 6 belongs to ideal prime ideal generated by 3. So we have to omit those and so on. So I hope this is clear now. If, I mean, if there are any doubts, please let me know. Otherwise, I will. And this is d of 6. I'm just writing. Okay, clear. Great. Okay, so I will move to now next question. So prime ideals doesn't intersect with which we are inverting. Exactly. That's what this means. That's what this is, that it should not intersect with the ideal. So prime ideals are exactly those where they are not in the intersection of this. I mean, let me highlight this with different color. This. Okay. So it should not intersect with the idea elements which we are intersecting. It should not intersect with the, I mean, our multiplicative set with which we are localizing the ring. So yes, it should not intersect with the inverting elements. Yes, that is the, what I can say, identification of prime ideas in the localized ring. Okay, so we'll move to next question. I hope it is okay, clear. True or false. Again, we have to check the following, that for every positive integer n, so n is any positive integer, does there exists an integral domain with exactly n prime ideals? And any guesses? For any given n, can we generate, or can we have integral domain such that it has exactly n prime ideals, or that is not possible at all? Okay, can we give an n such that there exists integral domain for such that that's not possible. We cannot have any integral domain containing exactly that many prime ideals. At least any guess that whether this is true or false or anything on that line? Um, so this is related to this question or the earlier question? Okay. Okay. Euler phi function. I mean, actually, we will be using primes to generate this. And we have to actually create. So the answer to this is true. Let me write here true. Okay, and we will see like how we can generate. So for n is equal to 1, can you give me some integral domain which has exactly one prime ideal? Okay, Z2 is good. I mean, but yeah, I mean, it's not, we can take any field, right? Only ideal, only non-trivial Z2 is okay, but we can take any field K and only non-trivial ideal. In fact, only non-trivial that is also maximal and that is also prime ideal in K is ideal generated by 0. That's it. Is it okay? So it has exactly one prime ideal for any for field. It contains exactly one prime ideal, and that is our maximal ideal, and so on. And that is 0 ideal. So n is equal to 1 case is true. And what about n greater than n greater than 1? Can we generate? So we have to make use of, since they are asking about integers, we know how primes look in integers. They are exactly prime numbers. So we will, that's why generate that in Z, okay? So consider Z and choose prime P1 to Pk or Pn minus 1 fixed. Choose primes. Choose primes. Okay. And then what we do this? This is A in Z such that Pi doesn't divide A for all I from 1 to n. Okay, so we are taking all the integers such that none of this prime integer divide that integer A. So this is multiplicative set. That S is check, S is multiplicative set. Clearly 1 belongs to S, right? Because no Pi divides 1. So 1 is there. Good. Now suppose A and B belongs to this S. This implies Pi doesn't divide A for all I from 1 to n. And Pi also doesn't divide B for all I from 1 to n. Okay, so this implies n minus 1. Okay, we are working with n minus 1. N also doesn't create any problem, but let us do this. So this implies this Pi won't divide A and B because Pi's are prime. Okay. So far we are good. So this implies this AB belongs to S. So this S is a multiplicative set. That is not a problem. So now we consider this ring R S inverse Z. And what are the prime elements here? So prime ideals in R, again, as we said, that prime such that they should not intersect with this multiplicative set. So prime ideal are such that they are prime ideals in Z such that prime ideal, let me say, prime ideal P in Z such that P intersection this S is empty. Okay. And can you tell me what are the primes which does not intersect with this S? These are exactly this n minus 1 ideals, right? Because any other element, any other prime you take, it will always intersect with this S. Because none of these primes will divide that new prime, and then that element will belong to this S. So therefore, prime ideals in R are this S inverse P1. When I'm writing P1, it means ideal generated by this, or let me just write this P1, S inverse P2, so on up to S inverse Pn minus 1. And also 0 is still my prime ideal because we are in integral domain. So 0 is prime ideal. So therefore, this R contains exactly n prime ideals. Any doubts here? We generated a multiplicative set such that it will omit those n primes, which will give me the set spectrum in the localized string. Any doubts? So this was okay. It was because we were working with the integral domain here. Can you quickly give I mean a ring where only n many prime ideals are there, and I mean it need not be integral domain and so on. I mean, since we wanted integral domain, that's why we use localized ring to obtain prime ideals. But do you have any quick example in mind, which if you can, if it is integral domain, good, but it's okay if it is not an integral domain. Okay, so this was integral domain. So for non-integral domain, I mean, this is very bad way of writing it, but let me just write R not an integral domain. In that case, we can choose this R to be K into K into K, where K is filled. And all the prime ideals here are of this form. 0 cross K cross K, or some K cross 0 in some ith place cross K. Okay, so it has exactly n prime ideals. Okay, and you can check this. Only prime ideals of R, or prime ideals, or let me just write spec of R is equal to K cross 0 cross K ith position I from 1 to n. Okay, and this has exactly n prime ideals. You can check this. But this is not an integral domain, okay? Because this 1 comma 0 into 0 1 0 is 0 0 0. So this is not integral domain but the question was asking us about the integral domain. I mean, we gave them the integral domain which has exactly n ideals, but this is a quick example where we have exactly n prime ideals. but the ring is not, unfortunately, not integral domain here. So any doubts? I mean, of course, if n is equal to 1, then it is a field. That's very trivial. But apart from that, if n greater than 2, it's not integral domain. So any doubts here about this second half where I was talking about non-integral domain rings? Okay. So Q expansion equation y. We want K prime ideals. Is this example fine? Okay. I mean, it has more than, okay, xn power xn minus k square. Okay, but since there are n variables, x1 ideal generated by x1 is prime, right? X2 single ideal generated by x2 is prime, ideal generated by xn is prime, then ideal generated by x1 comma x2 is also prime, and so on. So there are more than n. In fact, there are many more prime ideals in the ring you have given here. Do you understand? I mean, we can take x1 is not. Yeah. Okay. Yes, exactly. So x1 is a prime ideal there. That's not a problem. It is not integral domain anymore, but it is still a prime there. Okay, so there are many more prime ideas there than which you mentioned. So yeah, I mean, you can think and you can definitely generate many more. I mean, you can consider it as an open exercise where you want to generate integral domains. I mean, this is of course example of not integral domain, but you can also find, I mean, try to find rings where we can have exactly n many prime ideals. Don't care about whether it is integral domain or not, and so on. And think about it, okay? So I hope this is fine for others also. Divya, is it okay? Okay. So we'll move to next question. And so the question is, now let R be K, X, Y, Z. So it is polynomial ring. And I is this ideal generated by XY, XZ, and YZ. Okay. And they are asking true or false that the cardinality of min R mod I is 4. Okay. So this min R mod I is set of all minimal primes of R mod I. So minimal primes means um, they are minimal in the spectrum of R mod I. Minimal with respect to inclusion. And in this case, these are in fact prime ideals which are minimal and contain I. So if I want to look at this spectrum of R mod I inside spectrum of R, so it is all the prime ideas which contain I. So we have to see the minimal among those which contain I. Uh, uh, is the definition clear? So they're talking about the cardinality of minimum R mod I. So in short, we have to find, so kind of find min this min of R mod I. Okay, so what is it? So note that this I here, this xy, comma yz, xz is monomial ideal. Okay, and one result which I will use here, you will learn about this in like next week or maybe next couple of weeks, where you will learn about primary decomposition. And there you will see this, that if we have this fg in R and this gcd of f comma g is 1, then this I comma fg is if comma ig. Okay, so this is happening only because this I is monomial ideal. Okay, you can, I mean, you will see this result in upcoming week maybe, but we will use this in this question. Assume this for now. So what they are saying, this we can split the ideal where GCD of this f and g is 1. So here we have xy, xz, yz. So since GCD of y comma z is 1, I can simply write this is as xy, xz, comma y intersection xy, xz, comma z. Is this okay? Just using this above result, and GCD of y and z is 1 in polynomial ring. And since y is there, I can remove these elements. Since y is here, I can get rid of this. Not x is not correct. So we do not need this as we have this here. And similarly, since z is here, we can omit this. So we get this xz, comma y intersection xy, comma z. And again, I will use this to split these two elements, and I will write this quickly. If you have any doubt, please let me know. Okay, so this zy and zy, one of them can be omitted, and I get this intersection xz, intersection yz. Is this clear? So these are definitely prime ideals. We know that this xy, xz ideals generated by variables are prime. Okay, so these are prime ideals. Let us call them P1, P2, P3. Now we have to check whether, so these are definitely, so I can write this, not, I mean, P1, P2, P3 are prime ideals containing I. Now to check whether these PIs, or let me write P1, P2, P3 are minimal primes of I or not. Minimal primes over I. Okay, so it is called as over I. Over I means prime which is above this ideal I. So it is like P is here I. So these primes are primes over I. And we have to check the minimality. So how to check that? That suppose there exists Qs over I and we have I contained in Q contained in P1, suppose. Okay. So this implies I contains what? P1 is what? My x comma y here. Okay. So I want to check whether we have to check all these three, whether they are minimal primes or not. So let us check for P1, which is x comma y. Okay. Okay. So I have this. So I contains what? Xy. Xy belongs to Q, which is contained in P1. Okay. Since let me write this. Xz belongs to I, which is contained in Q. Q, there exists prime. Okay. This is prime. Q over I. This implies X belongs to Q. And again, we have YZ belongs to I. which is contained in Q. This implies Y belongs to Q because this is contained in P1. Okay. So these imply what? This X comma Y belongs to Q1, which is X comma Y. Okay. So this Q is in fact X comma Y. So therefore P1 is minimal prime. Any doubts? We just started with some prime ideal. We considered that prime ideal to be contained in P1, and this Q anyway contains I, since we are considering it to be prime ideal over I. And we saw that we are considering this condition that this Q is contained in P1. Okay, so XZ is an element of I. So since X belongs to Q or Z belongs to Q, since Q is prime ideal. But Q is also contained inside P. So since Z does not belong to P1, X has to be in Q. Okay, since Q is contained in P1. And similarly for YZ, we get Y contained in Q. So this ideal generated by X and Y is contained in Q. But Q is contained in P1, which is ideal generated by X and Y. So therefore, this Q is in fact ideal generated by X and Y. So, which is P1. So therefore, P1 is minimal prime over I. Any doubts? And similarly, I mean, on the similar lines, you can get that. So if you check for, again, P2, which was, I guess, XZ, you can again start with the I contained in Q contained in this P2, and you will again end up getting that this Q is equal to X comma Z. Use similar argument as above, and again we can check this P3 to be X comma, I guess, Y comma Z, and again start with this, and you will again end up getting this Q is in fact Y comma Z, and this entirely will prove that this XZ, XY, YZ are minimal primes over I. In fact, they are minimum of R mod I, R, XZ. Because anyway, ideals, prime ideals of R mod I are all the prime ideals containing I. We know that. And these are anyway all, and these three are anyway prime ideals which contains I. Okay, so this is XZ, YZ, or let me write this. I, YZ mod I, X9, XY mod I. Okay, so therefore min of cardinality is 3. So this is false. And this is in fact equal to 3. Okay. Any doubt? In the definition on anywhere, uh, I would like to share the screen and to show you what is the code for Macaulay 2 in to calculate minimal prime. Okay, so since we had this ring, I hope you can see this screen. S is equal to Q, X comma Y comma Z. This is my ring. Okay, and I am generating this ideal x star y star z, and x star z. Okay, and this is the code for minimal primes of I. And it gives me exactly this three ideals. Okay, and you can try this for any ideal. Okay, this is the ideal, and minimal primes are just these ideals. Ideal generated by x, ideal generated by y, and ideal generated by z. So it requires only this code, minimal primes I, and it gives list of minimal primes of ideal I. You can try this and see. So if you don't want to actually calculate this by hand, but it's good to have a practice. So you can use this minimal prime code for Macaulay too. Any doubts here? Not, then we can go back to our notes. Please let me know if there are any doubts. Otherwise, I will go to next question. So now we have this. Suppose R comma M be Noetherian local ring. So Noetherian local ring means it is local ring. Local ring means it has only one maximal ideal. And Noetherian means it satisfies a ascending chain condition. That is, every ascending chain of an ideal terminates somewhere. When I say terminates, it means that all the ideals after some point becomes equal, or equivalent condition to say that a ring is Noetherian is saying that every ideal in that ring is finitely generated. Okay, so we have this Noetherian local ring. So it is Noetherian ring which has exactly one maximal ideal. So they are saying, so in this condition, they are saying that suppose it is a Noetherian local ring with at least two prime ideals with maximal ideal M anyway. So this M is this M and this M are same. Okay, this is the maximal ideal of Noetherian ring, and now they are asking this true and false, that there does not exist a positive integer t such that this m power t is equal to m power t plus 1. So any guesses? So what they are saying is, it is a Noetherian ring. It has an Noetherian local ring. So it has exactly one maximal ideal. That is not that's not a problem. But now they are saying that it has two prime ideals. it has at least two prime ideals. So it has maximal ideal only one, but it may have multiple prime ideals. So it is saying that it has at least two prime ideals. So they are asking us that does there exist any integer t such that this m power t is equal to m power t plus 1. This condition they are asking us to check whether this is possible. Okay, so suppose we will see that, suppose if there exists, do we get any contradiction, or can we actually prove that it exists or not? So suppose there exists n such that m power n is equal to m power n plus 1. Okay, but note that ideals in a ring can be considered as modules over that ring. Is there in doubt? More ideals are always module over that ring. And apart from this, since our ring R, since R is Noetherian, this M and in fact all the powers of M are finitely generated. Finitely generated as an ideal and also finitely generated as a module also. So these two conditions we have. So does this remind anything to you? If not, then let me recall this to you. Nakayama Lemma. And what it says that if R comma M is local ring and M is finitely generated. So this Noetherianness here actually took care of this M being finitely generated. And what this statement says that if M is equal to M into M, then M is 0. This is the statement of Nakayama Lemma. So what we have is, if there exists n such that m power n is this m power n plus 1, then I can look at this as m into m power n. Okay, and this is maximal ideal of local ring, and this m power n is finitely generated ideal because we are in Noetherian ring, and therefore finitely generated as OR module. Okay, so then by Nakayama Lemma, m power n is 0. Is this okay? This much we have. So we are given also the info. So if I take this, any P in spec of this R, then 0 belongs to this P. This implies this 0 ideal also belongs to P. But 0 ideal, when I'm writing this 0, this is this m power n contained in P. But once I have m power n contained in P, this implies m contained in P, right? Because this P is prime ideal. Okay, so if some ideal contained in prime, its radical is also contained in prime. Okay, so but M is maximal ideal. So these imply what? That this P is in fact M. So this implies that P is, so we started with some prime ideal in spectrum and we didn't specify anything. We just took an arbitrary ideal in a spectrum, and I got that P is equal to M. So these imply what? That P is unique prime ideal in R. In fact, this P is actually M. Okay, so but this contradicts the fact that there are there are at least two prime ideals in R. The information was that given ring R has at least two distinct primes. But if this happens, that m power n is equal to m power n plus 1, then using Nakayama Lemma and prime properties of prime ideals, we end up getting that in that case, that ring will have exactly one prime ideal. But our ring R has at least two prime ideals. So therefore, no therefore, let me just write it like this. There does not exist any n in n such that m is equal to, m power n is equal to m power n plus 1. Any doubts here? So, but this also, I mean, just an observation that this means that m is properly contained in m squared, properly contained in m cube, and so on. So this chain is descending at every step. Okay. Any doubts? This is descending chain. Okay. This is not ascending chain. Noetherianness talks about the ascending chain. So this is descending chain. And if I have prime ideal, if I have Noetherian local ring with at least two prime ideals, then these powers of M are properly contained in each other. And they do not become equal at any stage. I mean, that's what this statement implies. So any doubts anywhere about how we are applying Nakayama lemma, or how this section, in fact, this part? If you have any doubts, please let me know. Otherwise, we can move to next question. Okay, clear. Great. So this is next question. So question again, this is true or false. It says that R has non-trivial idempotent element, then R is direct product of two rings. So when we say that R is direct product of two rings, it means that we want to show that R is isomorphic to direct product of two rings. I mean, if you can show that it is exactly equal, that's okay, but isomorphism is good enough. And it need not be equal to always. So R has non-trivial idempotent elements. So idempotent elements mean, I think, idempotent. So an element E in R is called, think we did something related to idempotent last lecture also. Reverse direction is true. And what about the forward direction? So reverse direction is true. So can you give me a non-trivial idempotent element in the reverse direction? So let us check whether this is if and only if. Since the reverse is anyway true, so let us check for yes 1, 0. That is true. If e square is e. Okay, so what Subhadeep is saying that this is in fact if and only if statement, which is true. So let us see the converse. So converse is that R is direct product of two rings. Okay, so what are trivial idempotent elements here? It is 0, 0 and 1a, 1b. Okay, so what Subhadeep is saying that since this is isomorphism and these two are different elements, now consider this 1a, 0. This is also idempotent because 1a, 0 square is 1a, 1a, 0, which is again 1a square, 0, but 1a square is 1a, 0. Therefore, this is idempotent element. And since this is isomorphism, 0 goes to 0, 1 goes to 1 of this ring. But this element 1a, 0 will correspond to some element in R. So let us call this alpha. So alpha will corresponding to some 1a in 0, such that if I call this isomorphism phi of alpha is 1a, 0. But this imply what? That phi of alpha square is phi of alpha into phi of alpha, which is 1a, 0, 1a, 0, which is 1a, 0. But this is what? Phi of alpha. But this is isomorphism. So these imply alpha square is equal to alpha. So this becomes that alpha is idempotent. And in fact, under isomorphism and under homomorphism of rings, idempotent actually goes to idempotent. Because this will always hold in that case. So, okay, it has non-trivial idempotent element and it won't be equal to 0 and 1 because of the isomorphism between the rings. So we have this, but what about the actual part, if then part, that if R is ring with a non-trivial idempotent element, can we express it as direct sum of two rings or direct product of two rings? So let us start. Statement is true, by the way. Let me write it here. It is true. And we are now proving it. We already, as Subhadeep suggested, we already got the converse part. So let us prove the front part. That R has idempotent element. That is given. Non-trivial. Let me write here non-trivial. Say E. Okay, so we have E square is equal to E. And now consider this ring, RE. Not this set RE, such that R into E and R in R. Can you see this set as a ring? This is definitely ideal generated by E in my ring R. But can you see that this RE is itself a ring? This RE has a ring structure. Can you give me multiplicative identity in this set RE? So I'm saying that RE is a ring. It need not be Yes, need not be subring of R. Okay, so what is multiplicative identity here? But note that R into E is what? R E square. Oh, we have these elements. When I multiply this by E, so it is actually 1E, which is RE into E. So RE square. So it is RE because E square is E. So therefore, RE is a ring. It satisfies addition and product property. That's not a problem. Okay, it definitely satisfies addition. Addition is not a problem. We will also see is a ring as RE into SE will be RSE square, which is RSE. And addition is clearly not a problem because RE plus SE will be R plus S whole bracket into E. With multiplicative identity, with multiplicative identity E. Okay, and similarly, as Subhadeep again pointed out, this 1 minus E, now again in R, I'm writing here in R to avoid the confusion when we are in R and when we are in RE. So in R again, this 1 minus E square is 1 minus E into 1 minus E. So which is 1 minus 2E plus E square, but E square is 2, is again E. So it is 1 minus E. So 1 minus E is again an idempotent element in R. So similar, so this when we calculated here, this whole explanation for RE becoming ring is true for any idempotent element. We not anywhere use specification of E. So similarly, we will have this 1 minus E R as what I can say is a ring with multiplicative identity, or let me write it like this, multiplicative identity again 1 minus E. So RE had multiplicative identity E. R1 minus E will have multiplicative identity 1 minus E. So can you give me the, so our claim is that R is isomorphic to RE cross RE minus 1. Can someone, or 1 minus E, can someone give me how the map will go? So this is isomorphism. So we have to define some phi from R to RE cross R1 minus C, and to show that it actually gives isomorphism, ring isomorphism. Note that this RE and R1 minus E are not subrings of R. They are rings in itself. Because if we say that something is a subring of, if I say S is a subring of R, then this S must have same multiplicative identity as a multiplicative identity of our parent ring or the bigger ring R. But in this case, when I am writing RE as a ring, it is ring in itself. It is not subring of R, because RE has a multiplicative identity as E, whereas multiplicative identity of R is 1. Okay, so they are not, I mean, RE and R1 minus E are not subrings of R. They are independent rings, which has independent ring structure. And even RE and R1 minus E are not related to each other. They have independent ring structure with multiplicative identity E and 1 minus E respectively. So we define this ring homomorphism RE, R1 minus E, and see how things go. To check now that we will see that this is a ring homomorphism. So enough to, not enough, but let us see how kernel looks. So it is R such that RE, R1 minus E is equal to 0. So when I write this 0, it means 0, 0, right? So it is R such that RE is equal to 0 and R1 minus E is 0. This implies what? R such that RE. So since R into E is 0, R into 1 minus E is 0, their addition will again be 0, right? So R plus RE is equal to 0. So it is R such that, sorry, R is 0. So this is just 0. So therefore, P is injective. Injectivity was not a problem anyway. Can you tell me about surjectivity? What element of R? So to check surjectivity for SE or RE comma S1 minus E, we want to find T such that this phi of T is RE comma S into 1 minus E. Can you give me this element? What this T will be? Any cases for this T? See, we want to generate this T. Let us, so this T we choose T to be this RE plus S1 minus E and check what P of this T is. P of RE plus S1 minus E is what? RE plus S1 minus E into E, comma RE plus S1 minus E whole into 1 minus E. Okay, and now we will simplify. So it is RE square plus S into 1 minus E into E, comma RE into 1 minus E plus S into 1 minus E into 1 minus E. This is just, I'm applying the definition. And let us calculate what this is. 1 minus E into E is what? E minus E square. But it is what? E minus E, which is 0. So this term where we have product 1 minus E into E, and this term we have product 1 minus E into 1 minus E. This becomes 0, and this E square here is idempotent. So RE square actually becomes RE, and here this, in this second ring R1 minus E, this is multiplicative identity. So this now becomes 1 minus E again. So my this phi of RE plus S1 minus E actually becomes RE comma S1 minus E. So this proves the surjectivity of this map phi. Okay, so therefore R is isomorphic to RE cross R1 minus E. So any doubts here where E is non-trivial, idempotent of R. So is this clear? Okay. So this was something which we wanted to do, and apart from that, uh, this is next question. Question 8, again true or false, that spec R is disconnected, then R has, this is in fact if and only, R has non-trivial idempotent element. Okay, so any guesses here? So we already proved that if R has some non-trivial idempotent element, then R is isomorphic to R1 cross R2. So can we somehow use this? So let us start. We will actually use this part to prove this. So we will in short prove that spec R is disconnected if and only R is direct product of two rings. Okay, and that's what we will do. So let us start with first part, that suppose spec R is disconnected. Okay, so this will be a bit heavy compared to what we did so far, but let us try to do. So it is disconnected. So it means that spec R is spec of, sorry, not spec, V of I union V of J, such that V of I intersection V of J is non-empty, and yes, yes, they are maximal ideals. Yes, true. In fact, in uh, direct products, the prime ideals are exactly of this form. So at ith position, we have prime ideal and rest are our original rings. So that's how prime ideals in the direct product look like. Uh, so as you said, that is true. Okay. So we have this at least so far. So, but this V of I union V of J, since V of I intersection J is empty, must R2 and R must are M2 are maximal ideals. Okay. Yes, they are closed sets. Yes, they are closed sets in spec R. Yes. So, so this implied that I plus J. Okay, we are using this property here. That V of I intersection J is what? V of I plus J. And V of I plus J is empty, implies I plus J is R. So it implies that I plus J are co-maximal ideals. Again, this spec R is V of I union J. V of I union J is V of I into J. So we will be using all these properties here. So now nil radical of R is equal to intersection of P such that P in spec R. Okay, but spec R is equal to V of I union V of j from above, which is V of I into j, which is what? V of radical of ij. We know that. We know this. So this implies that radical of ij is contained in P for all P in spec R. I'm just going through the definitions. Nothing else. Spec of R is, this is our assumption, but this implies this, and this implies this, and this spec R is equal to V I J means that every prime ideal contains this radical of ij. So this implies this radical of ij is contained in intersection of P. P belong to spec R, which is nothing but nil radical of my ring R. Is this okay so far? I am just obtaining all the possible information using this, which which I will use. Okay, and now since we know that I plus j is 1, this implies I plus j is 1. This implies there exists a comma b in, a in I and b in j such that a plus b is 1. This is there, but since this is here, I into j, radical of ij, this implies that ab power n is equal to 0. So a into b belongs to I into j, and that is contained in radical of I into j. That is now contained in nil radical of R. So that's why this A belongs to I and B belongs to J such that AB is equal to 1 gives me that A into B power n is 0. Let me write this. Since A belongs to I, B belongs to J, implies AB belongs to IJ, which contains radical of IJ, which is contained in nil radical of R. Is this clear? So this implies A power n into B power n is 0. And I can choose, note that not both A comma B belongs to nil radical of R. Okay, so this A power n is non-zero. Either of A power n or B power n is non-zero, and I choose this n list. N is list such that this happens. Okay, and not both A and B are in nil radical, because if both the A and B are in nil radical, since if both A comma B belongs to nil radical of R, this will imply A plus B belongs to nil radical of R. This implies 1 belongs to nil radical of R, which is definitely not true because we chose this AB such that A plus B is 1. Okay, so these both are non-zeros. Okay, so let us choose this both A power n and B power n to be this ideal. Okay, and then I1 and J1, I and J is okay. I and J are co-maximal. Co-maximal means I1 plus I plus J is equal to R. If and only if radical of them are co-maximal. This result you can check. Okay. This you can check. Okay, so this I1 into J1 becomes 0 because they are contained in a nil radical. Okay, so Ij will be 0 because they are contained in nil radical. So then by Chinese remainder theorem, this will be isomorphic. We wrote Chinese remainder theorem last time. So I'm not writing this. So this R mod I becomes a non-zero. This R mod J becomes non-zero. And this radical of I and radical of J are co-maximal. This will imply this I into J to be 0. And I plus J are still co-maximal. And so on. So we started with this 2 I and J. And we end up getting this R as a direct product of these two. So these imply from again by using previous question that R has non-trivial idempotent element. And this co-maximality and I into J becoming 0 in the radical will help us to apply this Chinese remainder theorem. So this part is through where we started with the disconnected spectrum, and we have this that R is direct product of two rings, and these are non-trivial because see none of them is 0 at least. Okay, so we can choose this n properly such that none of them is 0. Oh, I gave them name. Let me write this. It doesn't matter. Oh yeah, earlier I and J were these different ideals, and now this I1 and J1 are different. Okay, so yes, I1, J1 are different. I and J were what we started with, and this I1 and J1 are these two ideals. So this I1 and J1 are radical, co-maximal, and this Ij radical of I and J are co-maximal, and so on. So these two are non-zero rings. These two are non-zero rings. Non-zero rings. So this is true. And converse, as pointed out by Shubhadeep, converse is trivial since it has non-trivial idempotent element. It implies R with R1 cross R2 for some ring R1 R2, and uh, then spec of R is, spec of R1 union spec of R2 because spec of R is in fact of this form P1 cross R, comma R2 a comma P2 comma R, R1 cross P2 where P1 belongs to spec R1 and P2 belong to spec R2. So converse part is follows trivially. So that is not any problem. So any questions here? How things are happening or anything? This you can check here by Chinese remainder theorems. These are non-zero rings. Even if non-zero ring is non-trivial rings. And you can see this. Any doubts? No doubts. Okay. So we will move to next question then. Please go through this again, and if you have any doubts, please raise question in the discussion forum. If not, we will move to next question. This is last question for today. And this is not like solving question. This is just like last week we couldn't actually go through elimination. So I will just quickly show you how Macaulay to code runs in to calculate elimination. So this is non-graded. This is question from non-graded assignment, last week assignment of week 3, and they are asking us to use elimination method to calculate the kernel of ring maps. Okay, so how exactly, so let me write this map P, K, X, Y, Z, to K in one variable T, such that X going to T cube, Y going to T power 4, and Z going to T power 5. And how elimination method works is that they say that suppose we have, so I'm quickly running through it. So if I have this xn going to k y1 to ym such that xi goes to gi, okay, then we have this phi, we can define this phi tilde from this k x1 to xn or k ym to ym x1 to xn to again same ring k y1 to ym such that yi goes to yi, that's not a problem, and this xi again goes to gi. Now the ring as now our domain is bigger ring, and then kernel of this phi tilde is this xi minus gi, x1 minus g1, x2 minus g2, so on, xn minus gn. Okay, this is there, and kernel of P then is this x1 minus g1, x2 minus g2, comma, xn minus gn, intersection with this polynomial ring k x1 to xn. So we are, so in this ideal, we eliminate variables yi, and whatever we are left with is my kernel of original map y. So let me just color this so that if this is my original map, then the kernel of this map is this. Okay, where, let me just, where kernel of this map and this, okay, this, and this is actually this intersection with this original ring. I hope this makes sense. So we have to do this. So we will see like how this can be done in Macaulay too. Okay, it has uh, this code. Let me share this screen. We define this map again. My ring is QQ x comma y comma z, and this T, let T be ring QQ small t. Then my map is F is equal to, as I pointed out earlier last time also, that when we have to define map from T to R to T in Macaulay 2, we have to write it as map from T to R. Okay, so it is like what we do in vector spaces. If we go from vector space M to N, our matrix is N cross M matrix. So something like that happens here. So this is 1 cross 3 matrix. So we are going from R to T, where 3 variables are going to 1 variable kind of thing. So TQ, T4, T power 5. Okay. And we will see what kernel of this map is. Let us check. It is this ideal. Okay. And now we consider this new ring S is equal to T, comma, X, comma, Y, comma, Z. Okay. And now I define this ideal J is equal to ideal X minus T power cube, right? Xi minus Gi, where Gi was the image of that ring. So my X minus T cube, comma, Y minus T power 4, Z minus T power 5. Okay. And now eliminate this T. I hope this T works like this from J. And these are two ideals I'm getting. And they are exactly the same ideals. Okay. So can you see this? The kernel of this map is actually eliminating this variable T from this ideal J, which had T in it. So it finds all the relation of X and Y which can get rid of this T cube and so on. Is this clear? And if you want, we can again, let me define this map in two variables where the codomain ring has two variables. Let me again clear everything to avoid overlapping of variables. And again, let me define this R to be QQ W X. So I'm doing this to show you like how things are done when we have to eliminate two variables from the ideal. So these two are there, and F is my map. Again, T to R, R to T, such that it is SQ S square star T, comma S star T square, comma, and T power 3. And now kernel of this map is again this ideal. And now I wanted to define this new ring which contain this S, T and this W, X, Y and Z. Okay. And my now J is this ideal. All the variables minus, so W minus S cube, S X minus S square star T, Y minus S star T square and Z minus T cube. I hope no error. Okay, so far it looks correct. And now I'm eliminating this S comma T from my ideal J. And I'm getting this ideal, and these two are again same ideals, you can see here. Okay, so it finds all the combinations of a polynomial which can get rid of this variable, this elements S cube, S squared, T and so on. So is this okay? How elimination actually works and how to calculate elimination in Macaulay 2. And this is actually true. Okay, so when you do this on these variables, y square minus xz and so on, you can see that these elements actually vanish there. You can do it by hand. I mean, the examples is nicely explained in the lecture. So you can go through it also, but and try to do for simple ideals by hand. That how uh, elimination works. Okay, and any doubts here? I'm stopping the Macaulay 2 screen for now. Okay. So any doubts for what about what we did today, or anything which was not clear from the lecture, or anything? Feel free to ask. The last class you gave how to find x square b by GCD. Kernel of second question. Kernel of second question. Let me check. I mean, you are asking me about the Macaulay 2 code, right? X square, last question. Say, are you talking about S polynomial? Okay, that, okay. You were asking about this x t power a and t power b, how it looks. Okay. So, in that case, in general, we can't find the expression, but when GCD of a and b is 1, in that case, this kernel of this map x going to t power a, y going to t power b is actually x power b minus y power a. That is there. When the GCD of these two terms is, what I can say, is not equal to 1, in that case, we can have many expressions such that powers of x and y can add it to can become equal, and it will give me 0. So for example, x square y, that x going to t square, y going to t power 4 was actually generated by x square minus y. Because in that case we had we had expression apart from x of apart from of the form x power b minus y power a. So when GCD of a and b is 1, in that case the kernel becomes exactly equal to x power b minus y power a. Other than that, we have to work, and I mean exactly what you wrote is correct here. So the answer becomes x power b by GCD of a comma b and y power a mod GCD of a comma b. So we are kind of eliminating the common factor between this t power to get the minimal generator of that ideal. Yes, so what you wrote is completely correct. That the ideal generate. So if I have map, so let me speak this explicitly. So if I have a map going from kx comma y to kt, such that x going to t power a, y going to t power b, then kernel of this map is equal to x power b by GCD of a and b, comma, minus y power a by GCD of a and b. And when GCD is 1, then it becomes x power b minus y power a. Otherwise, this expression gives us the kernel of that map. Yes, it is correct. Thank you. Yeah. Any more doubt here, or any question? If not, then we can stop. Otherwise, please ask me question, or you can write it in the chat or unmute yourself. Okay, so if you have any question, please post it in the discussion forum, and We will meet next week, same time. Thank you. I'm ending the meeting.